Hi, good morning, everybody. Before we start getting into logs, we're first going to do a little bit of practice with solving exponential equations. So notice on this page, I have it stated that you're supposed to do these without a calculator. That is very important. You should be able to do most of these in your head. There's maybe one on here that might require a calculator, but a lot of these you'll be able to just kind of look at it and reason your way through it mentally. Otherwise, you can use the strategy that you guys learned in Algebra 2 of getting the same bases and setting the powers equal to solve. So for example, if I look at this first one, 2 to the x equals 8, I'm sure most of you guys can figure out that x would be equal to 3. But if you wanted to try to get the same bases, what we do is look at the larger base and see if we can write it as the smaller base on the left side. So can I write 8 as base 2? Yes, 8 would be 2 to the third. So once I have the same bases, if 2 to the x equals 2 to the third, then x has to be equal to 3. So the same parts in the equation would be the same. So I recommend that you try pausing the video and trying as many of these as possible on your own, again, without a calculator. I have outlined this row in yellow because they all employ a similar strategy of using negative exponents. The ones in blue use a similar property. The row in pink down at the bottom, remember that we can rewrite radicals as fractional exponents. And that very last one is probably the trickiest one on here. So go ahead and pause the video and try to do as many as you can. All right, so walking through these, hopefully this first one you're able to do fairly easily. And again, if you have to kind of use your fingers, that's fine. 3 times 3 is 9, times another 3 is 27, times another 3 is 81. So that exponent would be equal to 4. And folks, one important, really important thing about this is notice that on these solving exponential equations problems, you can't really solve them algebraically. We're kind of using mental math and trying to get the same bases. So what I mean that we can't solve them algebraically, I can't divide both sides by 2 in order to isolate that x, because if I divided 8 by 2, that would give me 4, which is not right. So you can't solve exponential equations algebraically, and that's going to be important a little bit later once we start dealing with logarithms. So we're kind of using mental math or the strategy of getting the same basis to solve. So on this next one, 10 to what power equals 1,000? X would be equal to 3. You can count the number of zeros. 4 to the x equals 16. X would be equal to 2. So again, I can't divide by 4 because that would leave a floating exponent. So algebraically, we can't isolate that x. So we have to remember our exponent rules to figure out what it would be equal to. Same with the next one, x equals 2. Now on this one, as far as knowing perfect cubes and perfect fours, I'm not going to get into any really high number ones, but 125, 64, those are perfect cubes that you should become more comfortable with as we start working our way through this chapter. So 5 to the third equals 125. 4 to the third equals 64. So 64 is kind of unique because not only is it a perfect square, it is also a perfect cube. Now on this one, 1/2 to the x equals 1/8. If you were a little unsure on this one, think about the expansion. If I take 1/2 times itself multiple times, in order to get that denominator of 8, we would multiply 2 times itself 3 times. So x would be equal to 3. Same with on this one. If I think 3 to what power gives me 243, and again, if you had to use your calculator on this one or maybe do some mental math off to the side, that's fine. 243, I wouldn't expect you to know perfect fifths. Isn't something that I would put on the test, but if you use some scratch paper, you would be able to reason through that one. Now this one, 2 to what power gives me 32? That would be x to the fifth, or x equals 5, so 2 to the 5th. Now, in the next row, this is where we go back to our power rule that negative exponents give our base a bad attitude and send it to the downstairs or into the other location within a fraction. So on these ones, especially ones that involve fractions on one side and non-fractions on another side, this is one where I would actually use that strategy of trying to get the same base. So if I have 6 to the x and I have 1/6, how can I write 1/6 as base 6? This would be 6 to the negative 1. So now I have base 6 on both sides, and the reason why 6 to the negative 1 is equal to 1/6 is that negative 1 gives that 6 a bad attitude and sends it to the downstairs of a fraction. So then x would be equal to negative 1. On this next one, we have 3 to the x equals 1/9. So focusing in on the fraction's denominator, how can we write 9 as base 3? Well, 9 would be 3 squared, so 1/9 would be 3 to the negative second. So x would be equal to negative 2. On this one, we have 10 to the x equals 1/100. So focusing in on that denominator, how can I write 100 as base 10? 100 would be 10 squared. So how do I get 1/100? That would be 10 to the negative 2. So x is equal to negative 2. So again, folks, negative exponents don't affect the sign of the number, only the location of the base within a fraction. So then, following the same suit, this would be x equals negative 5. And this one might have thrown you as well. So if I look at base 8, the current power of this is 1. Now, if I look at that fraction 1/2 and I say, how can I write 2 as base 8? You might be thinking, well, wouldn't I have to cube it? If I cube the left side, I would have to cube the right side. So again, I'm not doing this algebraically. I'm not square root. I'm not cubing. I'm not squaring. All I have done on these previous problems is replace the base with something that it is equal to. So I don't want to cube both sides. I want to break both of these down to be a smaller base. So if I look at that fraction 1/2, how can I rewrite that as a base raised to a negative exponent? That would be 2 to the negative 1. So can I write 8 as the same smaller base as 2? Yeah, 8 is equal to 2 cubed. And let's not forget to put that x back in on that left side. So now I have a setup where I can solve for the exponents. If I have 2 to the negative 1x equals 2 to the third, then negative 1x equals 3. So x equals negative 3. Now, even though this is a non-calculator section, when you're working on the homework, folks, it's not a bad idea to just check yourself by plugging back in, because when you plug back into these equations, you should get something that is true. So if I have 1/2 raised to the negative 3, there it is. We'd get the positive 8 on the right side just like we intended. So don't forget, as you're starting to get comfortable with exponents again, that you can plug back in and check your work. So on this one, using a similar strategy, I look at that fraction and I say, how can I write this as a base raised to a negative power? Well, this would be 8 to the negative 1. X. Can I write 64 also as base 8? We sure can. That would be 8 squared. So x equals negative 2. Something else to note, on this problem, I actually could have taken this all the way down to base 2 if I wanted. So it doesn't matter what same base you get them to, as long as they are the same. Now, going to the smallest base possible, a lot of times that will make your exponents bigger, which can make solving a little bit more cumbersome. So I normally try to go to the bigger of the same bases if I have the option. Now, looking at this one that I have marked in blue, 1/2 to the x equals 1. If you started this one and were like, well, I can write this as 2 to the negative 1x equals 1, but then, can I write 1 as base 2? We can't. But before you jump in and say, no solution, because that's what everybody gets really excited about on this one, we actually can use our last of the power rules to figure out what this one is equal to. Anything to the 0 power, and I better trap that in parentheses, anything to the 0 power is equal to 1. So though this looks unsolvable by trying to get the same bases, that 0 property says that anything to the 0 power will give you 1. So x would be equal to 0 here, and also on this one below. And we'll talk about base e in just a moment. So looking at the next one, if I have e to the x equals just e, well, this e has an implied power of 1, so e to the first equals e to the first, so x would be equal to 1. Now, this next one, this is one that I definitely wouldn't expect you to be able to do without a calculator because it relies on knowing what e is equal to. Now, I want you to shift down below, and you can draw a big old cloud around this. This is not something I would ever expect you to memorize or know, but just in case you've never seen this definition before, I think it is kind of interesting to note how E is defined. So most of us know that pi, 3.14159, so we know that it's a non-terminating, non-repeating decimal, but knowing how these irrational constants are defined can be a little bit interesting. So draw a cloud around this. This isn't something you have to know. It's really kind of just for fun. E is defined as 1 plus, and this little sideways m means the sum of. The items to the right of that sideways m, the n equals 1 and the infinity, this tells us the starting value and the ending value of the sum. And anybody know what that exclamation point next to the n is? It's not an excited n. It is defined as n factorial. Those of you who have taken stats, you've probably seen good old n factorial before. And what n factorial, or any number factorial, means is the number times all of the positive integers below it. So for example, 1 factorial is 1. 2 factorial would be 2 times 1. 3 factorial would be 3 times 2 times 1, and so on and so forth. So we've got a kind of complicated expression here, summation notation, which those of you going on to calc, you'll see a little bit later, and we've got factorial notation as well. So how E is defined as is 1 plus 1 over n factorial. So our starting value of n is 1. So our first fraction that we're adding to 1 is 1 over 1. Then we add that to, continuing with a sum that goes to infinity, 1 over 2 factorial, or 2 times 1, then plus 1 over 3 factorial. Now, what's strange about this is this sum keeps going on forever. I keep on adding more and more fractions to this, but as my summation goes on, these fractions are getting smaller and smaller denominators, like 1 over 20, 1 over 100, 1 over 1,000, 1 over 1,000,000. So as I get further out into this sum, we start adding more insignificant numbers, and that is why we end up getting a rough estimate for our constant E of 2.718. So I wouldn't expect you to have this memorized, just like 3.14 for pi. So I wouldn't expect you to know this. So let's go ahead and find where E is on our calculator. So you'll notice right next to your 4 key, we have ln for natural log. We're going to get into that a little bit later. But above natural log, you have e to the x as a second function. So go ahead and hit second natural log, and that gives you base e. And notice that when you use that, it automatically prompts you to put in a power, whether that be 1, 2, 3, and that is going to help us figure out just what power will give us that nasty decimal on this problem. So I'm going to go ahead and try 3. Nope, too big. So second natural log. Let's try 2. Oh, there it is. So x would be equal to 2 on this one. So e and natural log have a relationship with each other, and we'll get into that as we start exploring logarithms a bit more in the upcoming sections. So important thing with e is it is an irrational constant similar to pi, and it is a base just like our other bases in this problem. So all of the same power rules still apply. So on this next one, e to the x equals 1 over e. So how do I give that e a bad attitude and send it to the downstairs? That would be x equals -1. Now, in this bottom section of problems, this is where we start getting into a little bit more complicated territory, and we're going to have to start using some of this exponential to radical form knowledge. So just looking at this one, eventually you'll get to the point where you can just tell that x is equal to 1/2. But until you get to that point, I strongly recommend rewriting these as the same bases. So looking at the smaller of the two bases, 3 to the first, can I write 3 as a smaller base? No. So that's just going to stay 3. Can I write 9 as a smaller base? Yeah, we can write that as 3 squared. So I'm going to replace the 9 with 3 squared. And then we've still got that power of x there. So now I have the same bases. So if 3 to the 2x equals 3 to the first, then we set the exponents equal to each other. 2x equals 1, and thus x equals 1/2. So the reason why I said this radical stuff is going to come back to haunt us is taking something to the 1/2 power is the same as taking the square root of it. Remember on the first page of notes, we said that this is power divided by the implied index of 2. So taking something to the 1/3 power is the same as taking the cube root. Taking something to the 2/3 power is the same as taking the cube root of something squared. So let's go ahead and take a look at this next one. 125 to the x equals 5. And again, a lot of times students want to try to just divide by 125. You can't solve an exponential equation by isolating algebraically. I can't divide by that 125 because otherwise then I just have that floating x. So instead, we want to write these as the same smaller bases. So 125 I can write as 5 cubed raised to the x. And then 5 has an implied exponent of 1. So now that I have the same bases, 5 to the 3x equals 5 to the first. We set those powers equal to each other. So 3x equals 1, and x is 1/3. And this is nice because on your calculator, we do have a way of typing in a square root using second x squared. But this is nice because knowing that taking something to the 1/3 is the same as taking the cube root, it actually allows us to check ourselves on those radical problems. So 125 to the 1/3 power, boom, and that gives us 5. Now, quick note, those of you guys using the older calculators, when you type in that caret button or the exponent button, you will have to enclose the 1/3 in parentheses. Otherwise, your calculator will just take 125 to the first and then divide it by 3. So older calculators, make sure you're trapping that exponent in parentheses. Alrighty, folks, on the next one, we've got 1,000 to the x equals 10. So 10 to the first. Can't break that down into a smaller base, but 1,000 we can break down into 10 to the third. So 10 to the 3x equals 10. So set those powers equal to each other. So 3x equals 1 and x equals 1/3. Now this last one, this one is the one I feel is the most challenging on this page because I actually have to rewrite both of these bases. If I look at 125 and 25, there's no way I can write 125 as base 25. So for example, if I tried doing 25 squared, that gets me way over 125. So I need to break both of these down into a smaller base, particularly base 5. So 125, I can replace with 5 to the 3rd. And again, we've still got that power of x there. And then 25, we can replace with 5 squared. So now I have the same bases, so we can drop those off and set the powers equal to each other. So 3x equals 2 and x equals 2/3. Now again, it seems a little unnatural. It's like, wait, so 125 to this nasty fractional power gives me straight up 25, and you can verify it on your calculator. It indeed does. All right, folks, so solving exponential equations, we do need to get the same bases, and this is our last bit of exponents we'll be doing before we move on to lesson D and start some basic properties of logs.